For our next contestant, can I please invite Mr. Apiwit? And his talk will be on Lenz's law and its application.
Oh, shit.
All right.
All right.
Good afternoon.
Hello.
Are you ready?
I hope so.
I hope so. Okay,
Yeah.
then. Shall we start?
Yeah.
All right. You may start.
If I take just a regular piece of paperclip and I drop it through an aluminium pipe, it will come out the other end as you would normally expect, right? But if instead I take a piece of neodymium magnet and I drop it through the same aluminium pipe, it takes it pretty much forever until it comes out the other end. And the question is, why does this happen, right? Well, the first guess that many people might have would be that this magnet somehow attracts to the walls of the aluminium pipe, right? But do remember that aluminium is a non-magnetic element, so the magnet can't really just stick to the walls of this aluminium pipe and slow down in that way. So there's probably something else that's going on that's slowing down the magnet. And in fact, there is. Two key things are currently happening here. Firstly, when you have something like a magnet, it will have something called a magnetic field. But in this case, it's not the fact that we have a magnetic field, which is important, but the fact that the magnetic field that we have is changing over time. Because we have a magnet which will be falling down through the tube, which means that the position of the magnet itself will be changing, and naturally, the magnetic field that it creates will also be changing with the position of the magnet. And when we have this change in magnetic field, it will interact with the free electrons inside the aluminium pipe and exert a magnetic force on it, causing it to move around in a loop. And when we have moving electrons, we have something called an electric current going around inside the pipe. And this is a process called electromagnetic induction. But it's not the entire story, because there's something else also happening here. Because now that we have a current running within the aluminium pipe, the second thing that happens is that this current itself will be creating another magnetic field, sort of like how an electromagnet works. And this magnetic field, that's created by this current, will be acting in the direction opposing the motion of the magnet itself. And so what we have now is we have a magnet falling down through the pipes, and as it falls, it will create a current within this tube, and this current itself will be exerting a magnetic field, creating a magnetic field and exerting a force on the magnet in the opposite direction of its motion, and hence slow the magnet down. This process is something called Lenz's law, and it's much more than just a neat physics trick you can show your friends at a birthday party, because there's actual applications in real life. Because if you can slow something like a magnet down a tube, why not try to slow other things? For example, trains or roller coasters. And this is the same process that you'll see on things like magnetic braking systems, which do use in trains and roller coasters, for example. And so do spot out for them the next time you ever ride a roller coaster or even go on the SkyTrain later on today. Thank you.
All right. The timing is very spot on. Just about right. All right. So, now to the judges. Any comments from you?
I don't know how to start, actually. In that magnetic fields that you have, that is, you have to keep changing first inside that the tube, and it can create something flows
a force,
in there.
Right? So
is there a way to, like, make the analogy of that? Maybe it's easier to see about.
Okay, so there's a couple of ways that, like, you can have a magnetic force, right? So one way is you have a stationary magnetic field, which is like just a magnet like lying there.
Right.
And if you have, for example, something like a charge running around it, but the charge has to be running, it will create a force on the magnetic field, right? That's one way that you can have such magnetic field. But in this case, we're sort of flipping the things that is moving. So rather than moving the charge to create the force, instead we're moving the magnet, and the force sort of just stays still within the tube itself. And when we have the magnet sort of moving, it creates, as viewed from like the electron, it will seem as if like the magnetic field is changing, and which is like what creates the force like upon the electrons itself.
Yeah. It's like maybe you create another magnet that sort of pushing it around.
Like, yeah, in this case, because ultimately what you're doing as you, like the magnet falls down is you're creating a current, right? And that's just basically how electromagnets work. Because electromagnets, how it works is you run an actual current through a piece of coil, and that itself will create a magnetic field. But in this case, we're not running like an electric current through this, but we're creating an electric current in a different way by dropping the magnet through itself, and then that creates a current, which then ultimately creates the magnetic field that opposes the original magnet.
That's easy to understand.
Comment. I liked it I liked it.
Thank
I
you.
liked it particularly at the end when you mentioned applications in the sort of the world out there. So you mentioned the roller coaster and the BTS. Maybe next time, again, if there's a next time, might be nice to have a little bit more on that, on sort of the relevance of this outside the lab.
Okay.
But it's good.
Thank you very much.
So you say that it has been generated the current, right?
Yeah.
So can we measure if we have the multimeter to?
Okay. Because if you have a multimeter, you have to somehow like have the wires connected to this, so it might be a bit hard in this case. But I suppose if you have like an actual piece of wire and you wrap it around like this coil and you actually connect that to an outside multimeter, then you could probably actually measure the currents.
Okay, thank you.
All right. Any other comments from you, Dr. Rapi?
Well, actually, again, I liked your talk a lot again.
Yeah.
So I was wondering, so in this case, the magnet is being slowed down.
Yeah.
Right? What if you'd like to speed it up?
Okay, so this is interesting, right? Because the reason that the magnet itself is slowing down is because of another principle in physics called the conservation of energy. So what we're doing here, right, is as the magnet slows down, it transfers some of its energy to the electrons inside the tube in order to make it move around in a loop, right? So you can't, so in this case, if you think about it, you can't really speed up the magnet, right? Because as the magnet falls down, you'll need some energy to move the electrons inside the tube in one direction, but then you also need more energy in order to make the electrons, to make the magnet fall down the tube. And to make it faster, you need more energy. So you can't really just create energy out of nowhere, right? So in this case, you can't really make the magnet speed up. The reason whole lens law exists is, again, because conservation of energy, because energy needs to go somewhere, which is why the magnet transfers some of its kinetic energy into the electrons inside the tubes, and hence it will have to slow down.
All right. That's all the comments from our judges. So thank you very much.
Thank you very much.